We let Gargantua pull us down closer horizon. Then a powered slingshot around launching us towards Edmund's planet manually. Ever since we contrived a scientific understanding of the stars, we began imagining what it takes for humanity to achieve interstellar travel, but a cosmic dream crusher comes in the form of inconceivable distance. It takes light, the fastest thing there is in the universe, 4.2 years to only reach Proxima Centauri, the nearest star to the Sun, which is about 40 trillion kilometers away. Our galaxy, the Milky Way, is about 105,000 light-years across. So even if we could be able to travel at a significant portion to the speed of light, it would take us millions of years to travel through our galaxy. But what if there was a faster way? An unconventional approach to this problem entirely. Now, Einstein's theory, general relativity, is our best theory of space and time, and so it really is. You imagine space and time as a sheet. Literally a sheet surface, and all the theory says is that if you put matter and or energy into that, then it curves it and distorts it, and it can stretch it and make it shrink, and so it's the response of space and time to matter and energy. So the simplest version would be the sun. So you put the big spherical ball of stuff in there, and it warps space and time such that the nice straight line, something just traveling, minding its own business through that warp space, turns into an orbit. So light bends around the sun, and because it's just traveling through the curved space, the Earth goes round the sun because it's just rolling, minding its own business through the curved space. And that's basically Einstein's theory of general relativity, based on a solution of Einstein's field of equations and general relativity. Theoretical physicist Miguel Alcubierre proposed a speculative warp drive by which a spacecraft could achieve a apparent faster than light travel if a configurable energy density field lower than that of a vacuum could be created rather than exceeding the speed of light within a local reference frame. A spacecraft would traverse distances by contracting space in front of it and expanding space behind it, resulting in effective faster than light travel. In general relativity, one first specifies a plausible distribution of matter and energy and then finds the geometry of the space time associated with it, but it is also possible to run the Einstein field equations in the other direction, first specifying a metric and then finding the energy momentum tensor associated with it, and this is what Alcubierre did in building his metric. This practice means that the solution can violate various energy conditions and require exotic matter, so all you have to do, so those folded kind of geometries, is you have to try and specify how, where you would put the matter and what kind of stuff you'd put there to make the geometry fold, and that way you can write down that geometry. It's called a warp drive geometry, so you can do that to have a warp drive. The question becomes, what sort of stuff would you have to actually put into the real universe to make it warp in that way? It usually turns out that it's the kind of stuff that doesn't exist. It tends to be weird stuff, like stuff that has a negative pressure or something like that. So stuff that has physical properties that are just bizarre, and that no matter our energy that we know of in the universe has to make the geometry happen, but you can still write the geometry down in Einstein's theory. You can do the calculations and you can see the warp drive. You can construct wormholes that connect distant regions of the universe, which you could use as time machines. There are papers published in physics that show the total mass needed to deform spacetime would be less than that of our sun, but no one was able to get around the problem of negative energy. That is until Eric Lentz. He discovered there was a special feature of the geometry of spacetime buried in the general theory of relativity, more precisely in Einstein's field equations, which calculate how a particular distribution of matter and energy deforms spacetime. Lentz specifically examined the assumptions leading to the negative energy requirements in Alcubierre's work. Like his colleague, Lentz began by analyzing spacetime, modeling the multidimensional substance as a stack of very thin layers. He found that Alcubierre had only considered comparatively simple linear relationships between the equations for shifting one layer onto the next, at this point choosing more complex hyperbolic relations which typically express rapidly changing quantities, resulting in a different warp bubble than the one obtained by Alcubierre. It still requires enormous amounts of mass and energy, but according to Lentz's calculations, only positive amounts. Lentz's bubble looks different from the one Alcubierre worked out in 1994. It consists of diamond-shaped regions of altered spacetime that resembled a flock of birds. Creating such a spacetime geometry in reality would involve complicated layering of rings and disks, not made of solid material but of an extremely dense fluid of charged particles similar to the substance found in the interior of neutron stars. Calculations by physicist Alan Everett showed that warp bubbles could also be used to create closed time-like curves in general relativity, meaning that the theory predicts that they could be used for backwards time travel. While it is possible that the fundamental laws of physics might allow closed time-like curves, the chronology protection conjecture hypotheses that in all cases where the classical theory of general relativity allows them, quantum effects would intervene to eliminate the possibility, making these spacetimes impossible to realize. A Possible type of effect that would accomplish this is a buildup of vacuum fluctuations on the border of the region of spacetime where time travel would first become possible, causing the energy density to become high enough to destroy the system that would otherwise become a time machine. Alcubierre discussed some of these issues where he writes, beware in relativity, any method to travel faster than light can in principle be used to travel back in time. The conjecture has not been proven. It wouldn't be a conjecture if it had, but there are good arguments in its favor based on quantum field theory. The conjecture does not prohibit faster than light travel, it just states that if a method to travel faster than light exists and one tries to use it to build a time machine, something will go wrong. The energy accumulated will explode, or it will create a black hole. A fascinating possibility based on a special solution of the Einstein's field equations is what is called an Einstein-Rosen bridge, or more famously known a wormhole. A wormhole can be visualized as a tunnel with two ends at separate points in spacetime. Theoretically, a wormhole might connect extremely long distances such as a billion light-years, or short distances such as a few meters, or different points in time, or even different universes. The first type of wormhole solution discovered was the Schwarzschild wormhole, which would be present in the Schwarzschild metric, describing an eternal black hole, but it was found that it would collapse too quickly for anything to cross from one end to the other. Wormholes that could be crossed in both directions, known as traversable wormholes, were thought to be possible only if exotic matter with negative energy density could be used to stabilize them. However, physicists later reported that microscopic traversable wormholes may be possible and not require any exotic matter, instead only requiring electrically charged fermionic matter with small enough mass that it cannot collapse into a charged black hole. Wormholes are consistent with the general theory of relativity, but whether wormholes actually exist still remains to be seen. So you fly to Australia from La and you have to go quite a long way around this edge of the Earth, or you could tunnel straight through and get there quicker, so you could go all the way around the edge, or you could take the shortcut. So you can do that in Einstein's theory, you can write down that geometry. So the first question is, can you make it? There's a second set of theoretical bits of theoretical work which if you had a wormhole, then what would happen if you tried to travel through it? And what seems to happen is that they become unstable the moment that anything tries to go through, so you get kind of a feedback, and so it collapses. The answer is we don't fully know, but most physicists think that even if they existed they would be unstable, and as soon as you even tried to transmit information through them, send a bit of light through, then there would be some feedback and they'd collapse. And ultimately the reason we don't really know absolutely is because you need what's called a quantum theory of gravity, and we don't have one, so we don't have the theoretical tools to be absolutely sure that these things would be unstable or don't exist in nature, but we strongly suspect that they don't. If they did, you could build a time machine. Stephen Hawking wrote a paper. The conjecture basically was that the laws of nature will be such that you can't have stable wormholes and you can't build time machines. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this. Music.